Right? Hello? Uh-oh. Echo going on. Hold on. Let me see if I can fix that. Right. Okay. Let's see. There are only 11 people so far. Give it a couple more minutes. So, how are things going? Did everyone submit homework 2? Looks like must have. Maybe some some of you are still submitting, which is why they haven't joined yet. So, any questions about the course so far? There was an interesting email that I got from one of you. I don't think he's here today, about homework 1 and the questions in homework 1, where I think one of the questions you were asked to identify which matrices were PSD, PD, and so on. And for homework questions, if you asked to ask a question like identify which matrices are PD, you can't just just write down A is PD, so B is not, and so on and so forth. You have to actually show your work. Okay, even if the question specifically doesn't ask that, that's always assumed in a homework assignment. And an exam, you have to be more specific, especially with multiple choice, and maybe you don't need to show your work in some cases. But for homework, you always have to show your work. You can't just write an answer. So I hope that's clear to you guys at this stage. Anyway, all right. So let's actually briefly go over what we were talking about in lecture 8. By the way, I'm not hearing anything from people, so
hear me, sorry.
Right? Okay, all right, good.
Can you hear me, Professor?
Yeah, go ahead.
How many more homeworks are there gonna be?
Oh, there'll be at least 6 homework assignments in all. So you have 3 homework assignments, and then midterm 1, and then you have 3 more homework assignments and midterm 2, and then there may be one more last homework, homework 7, which will be there will be no final exam, so that will be the last thing, of course. But I have to still think about that. I might spend the last 3 lectures after Thanksgiving break talking about applications, and I'm not yet sure what kind of homework questions I'll ask about that. So so homework 7 may or may not happen, but you'll have at least 6 homework assignments.
Okay. Okay, thanks. Are they gonna be weighted equally?
Yes. Yes.
Okay, thanks.
Okay, so and you'll roughly have like 7 to 8 questions in every homework. Okay, so we were talking about Newton's method last time, right? And basically, it's a generalization of the idea you might have studied in an early calculus class of how to find the solution to a nonlinear equation like a gx equal to 0, right? And we applied the same notion to get a Newton, the Newton method, for which the new iterative time k plus 1 is xk minus this Hessian inverse times the gradient. Okay, and you can interpret this in some ways as a gradient-based method, but of course it's not always going to be the case, because this Hessian, even if it's invertible, may not be positive definite necessarily. So you have to be careful about how you apply it. Okay. And then we spent a lot of time talking about the convergence of Newton's method. And what we saw is that under certain assumptions, of course, that, for example, F is locally strongly convex near X star, then we can actually show that Newton's method, and assuming that the Hessian is Lipschitz with some parameter L, then we can actually show that the Newton's method, as long as you start close to the to X star, you actually end up converging really fast, right? So it's just called superlinear convergence or order 2 convergence. Okay, so linear convergence is when xn minus x star goes at some number to the power n. So some number less than 1 to the power n, which is what we saw with under strong convexity, right? For just gradient descent with constant step size. Newton's method, actually, that n appears in a second exponent up there. So if this delta is less than 1, you have delta to the 2 to the n. And so basically, this is called superlinear convergence, okay, in the neighborhood of X star. Of course, you have to be, in order for this to work, we really need x0 to be close enough to X star so that this delta is less than 1, okay? And in your homework, you'll actually see an example, in your next homework, you'll see an example for which if you don't start close enough, if you start close enough, you actually converge to converge superlinearly to the minimum. But if you're a little bit far away, then you could start diverging. Okay, so this is basically Newton's method only works when you're really close to the minimum to start with, which is fine because you can use other procedures to get close and then apply Newton's method at the end, and that really speeds things up at the end. Okay. By the way, there was a little issue with, in the notes, and I fixed it in the post notes. But this is what we were discussing. Actually, when I was writing things down, I noticed in class that there might have been an error, but I thought it was what I'd written was okay. But you really need the gradient to be M Lipschitz. The strong convexity is not enough to relate xn minus x star to f xn minus f x star. Okay, because basically this constant here actually this is not little m. This is capital M if you assume that gradient is M Lipschitz in the neighborhood of X star. Okay. An interesting question is if the Hessian is L Lipschitz, which is the assumption we made last time, the Hessian being L Lipschitz. If the Hessian is L Lipschitz, does that mean that the gradient is also Lipschitz?
Yes.
Yes? People think that the Hessian is Lipschitz, the gradient is Lipschitz? Anyone want to give me a counter example? Just think of which is one-dimensional functions, for which the Hessian might be Lipschitz, but the gradient is not. Anyone? So take x cubed, right?
X mod x.
So if we take x cubed, what is that? Log x?
X mod x.
X mod x. I don't think x mod x will work, but modulus of x cubed will work because if you take, or actually just x cubed, because if you take the second derivative, which is the Hessian in that case, that's linear, and the linear functions are Lipschitz, but x squared is not Lipschitz. Okay, so just because you had the Hessian being Lipschitz doesn't imply that the gradient is Lipschitz. So you have to actually, if you want to relate the fxn to fx star using this this bound, you really need you need to further assume that the gradient of f is M Lipschitz. Okay, so under all those assumptions, you get this result. Okay, I think that's all we discussed. I actually did some examples of that, and talked about how you can modify the rule so that it works more globally. Okay. So any questions about that before we talk about today's lecture? All right, so today we're going to take a break from theory a little bit and talk about an application, okay? And this is an application that a lot of you might be interested in, as this is how you do gradient descent and neural networks. Okay. So again, I'm going to be talking about a very specific early form of neural networks, which are called feed-forward networks. Okay, but the ideas that we talk about today are applicable more generally. Okay. So what's a neural network? So it consists of neurons. Okay, and what are neurons? Neurons are nonlinear functions essentially. So they take as input, say, z, and then you go through some kind of nonlinearity sigma to produce sigma of z. And what are some examples of nonlinearities? You could have the sine function. Okay. Okay. But then you may want to smooth it out a little bit, make it make the function more differentiable. So an example of a neuron that's for which sigma is differentiable is a sigmoid. Okay. A sigmoid has this kind of form, 1 over 1 plus e to the minus z. Okay. All right. And then you have something called a rectifier linear unit, or ReLU. These are all examples of sigma. Okay? Actually, the capital U, the ReLU. And the ReLU function looks like this. This again, nonlinear is 0 until you get here. For positive values, it's just a linear function. Okay. So it's max of z and 0. And then this is called a leaky ReLU, where you allow for you allow for this little slope, even for negative values. So this is called a leaky ReLU. Again, all of these nonlinear units are used in constructing what's called a neural network. And depending on which kind of nonlinearity you use, you get certain properties. And you can show for a lot of these nonlinearities that the corresponding neural networks have good function approximation properties asymptotically, which we'll talk about that in just a minute. All right, so this is for a single input. If you take a single input and pass it through the z, you get sigma z. But what, and again, the z, of course, is just a real valued number in this case. But what if I give it a vector input? So for a vector, if I have a vector input into a nonlinearity sigma, or a neuron sigma, what the neuron does is, the operation is that you take the x's and combine them through a linear these linear coefficients w1 through wn. So this is just summation wi xi, but then you may also add something called a bias. So this is called a bias, b. Okay, and then you apply sigma to that. So and sometimes when you draw a neural network, okay, you don't actually explicitly put down this summation. It's kind of implied. So you actually just draw the neuron with a bunch of inputs coming in, and it's implied that you take a linear combination of the inputs like this. Okay, and so when we draw a neural network, this summation is kind of hidden in the neuron. Okay. So any questions about notation? Okay, so that's how we represent neurons. We're not come to the network yet, but I just want to say a comment about why do we add a bias? Okay, and as an example of why we might do that, let's look at what would happen if sigma is the sine function. Okay, So sigma takes the value +1 if W transpose X plus B is positive. W transpose X is bigger than minus B, and -1 if it's less than minus B. Okay. Now, if we didn't have the bias, we would actually just be comparing W transpose X to 0, and you actually, so if, and let's look at a specific application of you know, a neural net for classification. Then if you have the bias, okay, what you get is a hyperplane with that shift B, right? So W transpose X plus B equal to 0 defines what's called a hyperplane in Rn, which in the special case of 2 dimensions, for 2-dimensional input X, you get is actually just a line, right? So the hyperplane is a line, but higher dimensions, it's a plane. And so in this case, if I didn't have the bias, basically I would be forcing this line to go through the origin, okay? And I have a lot more flexibility if I can make the of course, the slope of this line is a function of the weights and whether where it intersects the axes is going to depend on the bias B. But if I didn't have the weights, I could only have planes going through the origin, and that may not give me enough flexibility in designing a classifier that divides the +1 inputs and -1 inputs. Okay, so bias turns out to be very important in the forming of neural networks. Okay, and this is only one reason for that. And in fact, if you have multi-layer neural networks, which we're going to talk about in just a minute, then we can actually divide this input space in more complicated ways and do what's called function approximation, right? And so let's talk about the structure of a multi-layer neural network now. Okay. So what's the structure? So you might have say a d-dimensional input. So x1, x2, say that xd. Okay, a d-dimensional input, and you have this bias. So the bias, for the bias, I'll just have an input of 1. Okay, and so there are all these weights. So all the weights that go to the first neuron, okay, will correspond to some vector. So all these weights will correspond to some W vector. And this is another set of weights going to the second neuron here. That's another W vector, and so on. And then finally, you have this a B vector that takes you from, or a B input that's going into each of these neurons. Okay, so I can take all of these weights, so all of these weight vectors here, and the inputs B going along from the 1 to the neurons, and put them into a matrix W. So I'll call that the weight matrix W, and I'll call this the weight matrix for layer 1. So I'll put a superscript of 1, and this layer number here is 1 for this first layer, 2 for this, and I could have capital M layers total. Okay, and so all those weights are there, and these B's that are going out of here, I'll put that as a vector B1. Okay, right, and then I get to layer 2. So what happens at the end of the first layer? I have a bunch of outputs. Okay, and the outputs, I can collect all of these outputs. Okay. The outputs of the neurons. I mean, there's always going to be a 1 that gets input at every layer. There'll be a 1 somewhere here as well. But I'm not going to look at the ones, just look at the output corresponding to these guys. So let's collect all the outputs here at this layer. And the outputs I'm going to call Y1. Okay, so Y1 is the set of outputs that come out of layer 1, similarly, Y2 will be the set of outputs that come out of layer 2. Okay, and then out of layer M, I'll get ym, and this ym I'll denote that as y hat, and I will see why we're going to call that y hat in just a minute. Okay, so you have capital M layers at the output of each layer. Okay, I'm looking at the output of the neurons. I'm going to call those outputs y, y1, y2, and so on. All the weights that are collected, so all the weights here in layer 2 are going to be called W2, and all these guys will form a B2. Okay, so that's the structure, right? So it could have multiple layers, and by the way, there's a reason why I didn't say how many neurons. So you could have multiple different numbers of neurons in each layer. So I could have a d-dimensional input, okay, and I could have some other d1 number of neurons in layer 1, d2 in layer 2, and so on and so forth. Okay. And if at the end of all of this, if I want to produce a one-dimensional output, then I'll only have one neuron in the last stage. Okay. So if I want a one-dimensional output, basically I'll not have all of these. I'll just have one neuron at the last stage. Okay. But in general, you could have multiple neurons even for the last layer. Okay. Any questions about the structure of neural networks? Many of you probably saw this in some form when you took a machine learning class or something. So if you have any questions about the notation and the structure, just let me know now.
I have a question.
Yeah.
Is there one bias per xi?
So at each layer, you could have a one input that actually basically gets multiplied by the BIs to provide a bias term for each input of each neuron in the next layer. For example, so basically, the one here provides the biases for all the neurons in layer 1. The one here provides all the biases for neurons in layer 2, and so on.
Oh, I missed the one. Okay.
Okay. All right. All right. So we take all the weights on edges connecting layers m-1, little m-1, and m, and put that in a matrix W superscript m, which is exactly what I did here. This is W2, this is W1, and so on. And if I look at the ijth, the way I denote this is the ijth element of this WM matrix is the weight connecting the output J of the previous layer, m-1, with the ith neuron. So with neuron I of layer m. Okay. So if we look at, say, the let's go between layers 1 and 2, and let's look at the, say, the 2/3 element, or say 2/1 element of this matrix. Basically, I'm looking at 2/1 will be, I look at output 1, so output coming from this neuron, and what's going in as the input to the second neuron. That will be W21. Okay, and this guy coming here will be W12, and so on. Okay, and similarly for the B's. Okay, the first element of B2 will be the input going into the first neuron in the next layer. And the second element will be the second neuron in the next layer, and so on. Okay. All right. And the input of the network is the vector X. The output of layer M is denoted by ym. Now, I'm not going to be very specific about how many neurons there are going to be in each layer. So when I write down sums, I'm not going to write the upper limit with the assumption that the upper limit will depend on the number of neurons in the layer. Okay, so keep the notation a little less cumbersome. Okay, So the input is X, the output of layer M is YM. If I look at the output of the, let's look at the output of the first layer, the ith output of the first layer. The ith output of the first layer is sigma, say, so if you look at, like, look at this guy, this sigma is operating on all these inputs and producing something. So the linear combination of things that go into this nonlinearity sigma, I'll give that a special notation to make it convenient for when we do gradient descent. So I'll call that the input to the neuron at the first layer, the ith neuron, the first layer, yi1. The input, I'll call that xi1. But xi1 is given by the summation. It's a linear combination, and I'll take the weights basically going all the weights j from the xj's from the previous layer, but the previous layer is basically the inputs in this case, right? Just these inputs. So the xj's multiplied by wij of 1. And this summation is over j. Again, I'm not going to specify the limits of this sum because it'll depend on the number of neurons. Actually, in this case, I know in this case, j goes from 1 through d, but that's not important because we know that the input dimension is, we said, was d, but that's not so important. Let's just leave it as a summation over j there. And then I add the bias term bj1. Okay. So this is how I produce each output at the first layer. So these guys, this one, this one, this one. Okay, but you can write this compactly using a vector notation. So I'll put all the y's into this vector y1. Okay, and all these x's I'll call x sub 1. And x sub 1, this vector, I can use now just this matrix notation, w1 times x. Okay, that will produce in all of the components, right? So w1 times x. And then all the b's I'll put into a vector called b1. Okay, and this notation for sigma here is that this says that sigma is applied to each of the inputs, so separately. So that's my notation. So sigma applied to a vector of these x1s like this is going to be thought of as sigma applied individually to the components of these x1s. Okay. Again, it's a little confusing notation, but just to avoid having to write too many subscripts and so on. Okay, so this is sigma applied to each element of the x1 vector. Okay. Any questions?
A quick question.
Yeah.
Should the subscript on B in B sup 1 be I?
Ah, yeah, sure. Sorry. You're absolutely right. That should be I, not J. J was in the summation. Yeah. Pretty good. All right. So now let's go to the next layer. So what happens in the next layer? So let's go from y1 to y2, basically. So remember, we just saw that y1 can be sigma applied to x1 with x1 given by this. Similarly, you can show that y2 is sigma applied to the vector of inputs x2, where x2 is obtained by taking linear combinations of the outputs of the first layer. So that's y1 times the w2 matrix plus b2. So basically, going back to here, the y2 is obtained by taking linear combinations of y1s, applying the w matrix and the b's here. Okay, so this repeats for the remaining layers. With the last layer is sigma m, with xm being given by the linear combination of the m minus 1th layer plus bm. All right. All right. So what's the goal in building this neural network? Okay. The goal is to choose these weights, W1 through W capital M, and the bias terms B1 through Bm, so that the output of the last layer, which is also called the output of the neural network, approximates some desired function well. Okay, so basically we want y hat m, which is the y hat, which is the output of the last layer. I'm just going to call that y hat. I want that to be an approximation for some y, which is the output of a function that I don't know actually beforehand. So there's some function f, which if I had applied it to the input x, would have produced some number y. And this x is possibly multidimensional if y is multidimensional. But for our examples, we'll assume that y is just a real value to the output. Okay, so the input, of course, x is multidimensional, but the output may be scalar typically, but it doesn't have to be. It could be multidimensional. Okay, and what we're trying to do through the neural network is try and approximate this y, okay, for an input x. Of course, we don't know this function. Okay, so this f is unknown to us. And so we are trying to approximate this unknown function using a neural network. How can we do this? Why, you know, why will this even work? So anyone know what you would use to try and build this neural network so that you can approximate a general multidimensional function, f?
You minimize the sum of the square errors.
But of what though? You need something to start with. So what are you going to start with?
I think you need true values for your y.
Yeah, so the true value, so there should be some x's for which you know the true value of y. Okay, and even though you don't know f, you might be able to still determine. Okay, and this is the process of what's called labeling in machine learning, right? So you're going to use labeled so-called training data. And what's training data? The inputs for which you know the output. Which the output is known. So this, you know this output even though you don't know f. And if you took a machine learning class, you know how you might produce such label data. For example, if you're trying to predict house prices in a city based on demographic features like, based on features like the pollution level or the crime rate and so on. So you may already have a database of house prices for which you know those inputs, okay, from some other cities, okay? And you can use that to construct. You want to use that kind of label data to construct this function f to predict the house price of, say, a price of a house in Urbana that you're trying to sell. Okay, so that's an example, right? So you might be able to get labeled training data, even though you don't know what the relationship between those features, the x's and y, might be described through a very, very complicated function which you don't know beforehand. But you might actually know the outputs for certain inputs. And you want to use that information to construct a neural network that will approximate that function f. Okay, that's the idea. So we'll call the label data x1, the first, for some input x1, I know what y1 is. Okay, and I have these pairs. So I have x2, for which I know the y2. And say they're capital N points. I have that. Now we'll get to what Chelsea was just saying. So what we try to minimize through this training data is that we define some loss function that measure the closeness between your predicted output y hat and the actual output yn that you know from the label training data. So on your label training data, you look at what's called the empirical loss. And the empirical loss is the summation of the loss. Loss is just a measure of distance between the true output y and that produced by the neural network. Okay, so this is called a loss. L is a loss function. And a typical loss function might be something like a squared difference, right? Or the norm squared difference of y as the vector. Okay. So what is y hat n? Y hat n is the output of the neural network. I'm having trouble writing today. When the input is xn. Okay, yn is the output that you know from your label training data. Y hat n is what you get from the neural network when the input is xn, and you want this difference to be small across the entire training data set. So you want the summation of this loss to be small. Okay, is that clear? So that's how we're going to design the neural network to minimize this empirical loss on the training data. So how do we do this? Okay. So before we do that, actually, let's talk about some examples. As I mentioned, that if y is a scalar, L can be taken to be the squared loss. Although if you're doing classification, then y is a discrete valued output. So for something like predicting home prices in Urbana based on some inputs like crime rate and pollution level and so on, then the output can be considered to be a real valued scalar. But if you're trying to make a decision between say based on measuring some features of a patient, deciding whether they have a high risk or a low risk for heart disease, for example, then that would be a binary output, right? So in that case, then the square distance may not be a good measure, so you might use something else, like what's called a 0-1 loss, where the loss is 0 if you're correct, and the loss is 1 if you're incorrect. Okay, or you might actually replace that loss function with something a little more differentiable, and then there are examples of that, lots of examples of that that you can use. So this one, something called cross entropy loss, for example, that you can use in determining what the weights of the neural network should be. Okay, but let's take the example where y is some continuous output, and it's a scalar. In that case, you would just use y minus y hat squared. And if of course, if the output y hat is just a scalar, not a vector, the last layer has to have only one neuron. Right? And that's typical in many applications. So at the last layer, you basically only have one of these guys, okay, that produces a y hat. Okay, so we're going to assume that this L is, for now, although it doesn't, we'll study a little bit later in the course how to handle functions, how to do optimization with functions that are not continuously differentiable. But here we're going to assume that L is continuously differentiable. So for example, if it's continuously differentiable, then it rules out things like the 0-1 loss, right? And also we want this function eventually is going to be a function of the weights, and so this whole J is going to be a function of the weights and the B's through not just L, but also through the sigmas. So we have to assume the sigmas also are continuously differentiable, which means that would rule out all but it would rule out these three, and just only this one would work, right? Because none of these are actually continuously differentiable, because at the origin here the derivative changes, right? So well, it turns out that a lot of what I say will extend to beyond just differentiable functions, and so we'll maybe towards in the last third of the course, we'll actually talk about algorithms that one can develop for gradient descent that don't require that assumption. Okay, but for now, let's assume that L is continuously differentiable and sigma is also continuously differentiable. Okay, and this y hat n, remember, is just the y at the mth layer for the nth input, little nth input. Okay, so now J is a function of all these things. It's a function of all these weights, right? And the B vectors, we'll call them also weights, just not to have to call them, call everything that we are trying to optimize over as just weights, W's and the B's. Okay, so we want to minimize J using a gradient descent procedure. Because we know that's, at least so far, what we've talked about. We've spent a lot of time talking about gradient descent. So we want to use that to develop a way to minimize this function J. It's a very complicated function, right? Involving all these sigmas and various weights and the B's and very, very complicated weights. It turns out, although that because of the structure of the neural network, we can actually exploit the structure to compute the gradient efficiently. And that's what we're going to develop in the next few slides or next few pages. But basically, we need to compute the gradient with respect to all the weights. But since J is a sum, we can compute the gradient for each term in the sum separately, at least. So what we're going to do is compute the gradient. The gradient of this sum is the sum of the gradients. So I want basically the gradient evaluated at each training data point. I can compute them separately and then add them up to form the gradient of J. Okay. And what do we need to compute the gradient? So we'll need to take the gradient of L with respect to all the weights, Wij of, let's call that little of superscript L for each L I and j. Okay, for each layer and each weight in each layer, I need to compute the gradient, compute the derivative, and then also need the partial of L with respect to all the b i's for each I and L. Each layer and each I in that layer. So if I compute all these derivatives, I can put them all together into a large gradient vector. Okay, and that will be the gradient of one of the components in the sum, right? And I need to repeat that procedure for every data point. Okay, so but let's just focus on one data point, and we'll drop the n for convenience. So we focus on one data point, so one term in this summation. And let's see how we compute the gradient of L evaluated at that point, at that data point. Okay. Any questions? Okay, so let's take a short break before we talk about the procedure. Okay. Any questions? Okay, you can think about it a little bit more. We'll take a short break. It's 11:45 on my clock. 11:47 will reconvene.
Oh, hi, Professor. I actually have a question.
Yeah.
So it's actually a very general question. So basically, when you do like matrix level calculus, like what's the how to?
Oh, we were taught to take the gradient with respect to a matrix. Basically, we're going, but the matrix is just a collection of these weights, right?
Yeah,
so
that's right.
I can just spread them out into a vector, and then take the gradient with respect to each component, and then make a long vector out of it, and that's what I'll call the gradient.
So it's more like you convert the matrix form into some
yeah. Think of It's the matrix was just matrix notation here was just a convenient way to collect all the weights of a layer.
I see.
Think of that was the only purpose of putting it in a matrix, right? And so, but when I take the gradient with respect to all those weights, I can think of them as separate things. And I want the derivative with respect to each of those components.
I see. Okay. Yeah. Thanks.
Okay. All righty. All right. So is everyone ready to compute the gradients now? So the computation of the gradient is called the back propagation algorithm. Okay. And this allows this algorithm is an efficient way to compute the gradient for each data point, each training data point, efficiently by exploiting the structure of the network and also a very basic idea about computing derivatives, which is called chain rule, right? Which we've used extensively in this class already. So basically, if I want to look at, say, let's look at the last layer. Okay, I want to compute the gradient of L with respect to the ijth element of W in the last layer. But how is this loss function going to be a function of these weights? Okay, it's a function of these weights through the output, y, right? Because the loss function basically takes the output of the neural network and the difference between that and y, the true y, which you know for the training data point, and then computes, say, the square difference between those two. Okay, so that's how it's a function of the weights. It's a function through y, but then it's not just y that matters, but y is actually then related to to x. X is actually the one that relates the y and the weights, right, through this equation. Okay, so if we do chain rule, there are basically 3 stages. So we can first look at the gradient, the partial of L with respect to the ith component, y I m. Okay, and then look at the partial of y I m with respect to w I j. Okay, so this is just one layer of the chain rule, but now I know that y depends on w through x, right? So I'll further write this as times the partial of y I m with respect to x j m. Okay, because xjm is basically the one that contains the information of a wij, right? The jth neuron. So that's that times the partial of xj superscript m with respect to w ijm. Okay. Okay, so by breaking it down using the chain rule, I can now hopefully compute each of the components of this partial of L with respect to the Wijm. Okay, so let's see how we can do this. First, let's look at the first term, the partial of L with respect to Yim. You can actually compute this for each data point easily in practice. And the way you do that is, suppose, for example, and I just put a little example here, if y and ym are scalars and we use the squared loss, then given any input xn, yn, and so given any training data pair xn, yn, we can compute the partial of this quite easily at that data point. Has to be just basically 2 times y m n minus yn. Okay, because the square basically it's easy to differentiate. And even if you have other kinds of loss functions, as long as it's differentiable, this should be quite easy to do. So that this component, this is easy to compute in the last layer, right? by exploiting the fact that basically the loss depends on the output of the last layer and the true y. Any questions? Okay, so then let's see how we compute this guy, the second term, right? But that really is let's look at where that appears in the neural network. So let's maybe go back to the picture of the neural network. This is this last layer, and I'm looking at YIM. So YIM is produced by applying sigma to the XIM here. Okay, sigma to the XIM, and XIM. So if I look at the partial of YIM with respect to XIM, that's just the derivative of sigma. And I assume there the sigma is differentiable, right? I assume. I at least mentioned it, I didn't write it down necessarily. Which is just basically, it's called that sigma prime of XIM. Of course, assuming that, let me write that down here, sigma is differentiable. If it's not differentiable, we can use what's called a subgradient method, and we'll talk about that a little bit later in the course. Okay. All right. So what about the last thing now? The last thing is the derivative of the partial of xjm with respect to w. Something strange going on here. My notation. Yeah, sorry. It's yeah. So this should be xi. I don't know. I think this should have been xi here. Because the ith output only depends on the ith input, right? And that's how we define the neuron. Okay, so that's that. The xi sup m was defined to be basically the combination of the w's coming in, right? So to each of the neurons on the nth layer. So that shouldn't have been xj. That was xi. So. And we want xi with respect to WIM. Okay. Sorry about that. Okay. Yeah. So this is correct. So this is sigma prime XIM. I tried to avoid too many subscripts, but this is the minimum, the minimum that you can get away with, and you can still get a little confused by the subscript. So when you go back home and look at my filled in notes later, just make sure that you understand all the steps there. Okay. All right, so now let's look at XIM and how it's related to the YJM, right? Sorry, WIJ. So that's related to the outputs of the previous layer and these weights of the nth layer. Okay. So you take the linear combination of those guys and then add BIM to get XIM. So if you take the partial of XIM with respect to WIJM, so that will just leave this factor and all the other things will go away. So it'll just get YJM minus 1. Okay. Let's put it all together now. So we have this part, which we can compute given the loss function. Okay, and we have this part, which is a sigma prime, and this is basically YJM minus 1. So put it all together, this is partial of L with respect to delta YIM. Because if there was only one neuron in the last layer, there'll be only one I here to worry about. Okay. Sigma prime XIM and YJ. Okay. So that's how you would compute the partial for the last layer. So, oh, by the way, where do you get these quantities? This is XIM for say the nth training data. This would be XIM of n, right? So you basically give the input xn, and then look at the output of the or rather the input of the nth layer, and then look at the ith component for that. So that's how you get this. And similarly, this is the output of the nth layer for the nth data point. If I'm looking at the nth data point, so all these things are known for a given training input xn, the training data point xn yn. You know everything that happens at each layer, so you can use those to compute these derivatives. So you have this entire partial computed for that data point from that. But we are skipping these things just to be easy on notation. Okay. But remember that once we have this expression, this can be computed for every data point very easily, just from looking at what happens to that xn as it goes to the network. Okay, so now if you look at the partial with respect to BIs, that can also be done in a similar manner, exploiting the same structure. You do chain rule again. You take respect to YIM, and then YIM with respect to XIM, and XIM with respect to BIM. Okay, but if you look at XIM with respect to BIM, XIM with respect to BIM, you just get 1. Okay. So in this case, this guy is just 1. Okay, so to compute the partial of L with respect to BIM, you just use this quantity, which you can get from the loss function, and sigma prime XIM computed at that training data point. Any questions so far? Okay, so that's the last layer. But so back propagation algorithm, the power of the back propagation algorithm is in exploiting the network structure to make the computations for the previous layers, okay, convenient. You can do it iteratively, essentially. Once you know the solutions to the last layer, you can compute the solutions to the previous layer based on those solutions. And let's see how. Okay. So again, for say layer M, that comes before the last layer, what we can do is we still have the same kind of relationships. So to compute the partial with respect to WIM, I first look at the partial with respect to YIM, and YIM with XIM, and XIM with respect to WIG. Okay, so just as before, these two are easy to compute. So this is just the neuron. So this is just sigma prime XIM. Okay, and this is just like we had before. Using this this relationship here, you will get that this is equal to YIJM little m minus 1. Okay, so these two, this is just as in layer, just as in the last layer. Okay, but now let's look at how we compute this. So for the last layer, we just use the loss functions form to compute the partial of L with respect to YI sup M. We can't do that anymore in some previous layer. So how do we compute this quantity? So this is the key here. So let's look at how YM is related to XM plus 1. Well, it's related to this relationship to the weights, the weights at the m+1th layer times the output coming from the previous layer. So that's ym plus bm+1. Okay. So if I want to take the partial of L with respect to yim, I can take the partial with respect to the various components of X, because those have some relationship to the yims through this equation. Okay, so I'll take the partial of L with respect to the kth component of X m+1, and then take the partial of that with respect to yim, and then sum, because I know that there's this dependency here. Very good. All right, so how do I compute this quantity? Well, interestingly, we have actually computed this in the previous step, because if you think about it, I can write this partial as partial of L with respect to ykm+1, and then ykm+1 with respect to xkm+1. Okay, but this is just the neuron function that relates xkm+1 with ykm+1. So this one I know, this is just sigma prime applied to xkm+1. And this I computed in the previous step. Okay, because as I work backwards from the last step, in the last step I already computed del L yk capital M. So when I go to m-1, I can use that. I can use those computations for this purpose. Okay, so I already have these from the previous step. These are basically easily computed. So this is sigma prime, and then that last guy here is just wki, yes, wki m+1. Okay, from this relationship here, from this relationship. Okay, so then let's put it all together. So this is equal to summation. I'm just rewriting this times wki. Okay, so once we have these, we can basically plug it into this expression here, up here. So we already got these two. Now we got this from the summation here. So you plug that in, and you can compute the derivative with respect to wijm. Similarly, if you want to compute the derivative with respect to the b's, again, we'll use the partial with respect to yim, xim, xim, bim, but this is equal to 1 as before. This is sigma prime of xim, and this is basically computed right here in the previous step. So again, that's also useful in computing the partial with respect to bim. Okay, so let me just maybe put this whole page down for you and make sure that, so this is the key step, right? This is the key step in backpropagation. So how do you use the previous layers? Actually, I should say basically this is the key step. How you use the previous layers computed partials to actually compute the partial of L with respect to yim. And once you have that, then you basically computed all the partials of layer M based on things that you computed from the next layer, essentially. That's why it's called backpropagation, because you're starting from the last layer and going backwards to compute these derivatives efficiently. Okay, so you now have to do this. You do this derivative computation for every data point. Okay, and then you sum it all up. Okay, and that's how you get the gradient of L with respect to all the weights and the b's for your data set x1 y1 through x capital N, y capital N. All right. Again, it seems complicated, but it's actually very easy to program, right? And so once people had so when neural networks were first introduced, they were not very popular, and people didn't think they were that useful, largely because there wasn't the computational power to do this kind of gradient descent with large networks effectively. Okay, and you basically need large networks in order to approximate arbitrary functions well. Okay, and so and in fact there are theorems about that, but it turns out in practice you don't need as many neurons as predicted by the theory. That's a different matter altogether. But basically, once people had the computational power, then they could start trying these neural networks on real world examples and actually show that neural networks are actually useful in this kind of function approximation to predict outputs for based on some features. So basically, they've become the engine of machine learning now, right? And the key behind, okay, so why does it work why is it able to produce a good function approximation? And a key turns out to be the nonlinearity of sigma. So that plays a key role in actually being able to approximate an arbitrary function f. Okay. Okay. So this is a summary of the back propagation algorithm. So first you compute the partial of L with respect to YIM. Oh, sorry, what did I do there? Partial with respect to YIM for every I, and for every, this of course you do this for every, I should say all these steps are done for every data point. So you do this for all I, and then you go from the last layer down to the first layer and compute the partials with respect to the other guys like this. And then, and where basically you use the partial that you computed in the previous layer to compute the partial effect of YIM in layer M. Or I should say the next layer in the hierarchy, or the previous computation when you're doing it through backprop. Okay. Any questions? So you do all of this work just to compute the gradient, right? And you have to compute this gradient for every data point, sum it up, and you just get one. What can you do with this gradient? What you can do is basically do one iteration of gradient descent with this. So you do all of this work and you get one iteration of gradient descent, and you have to do multiple iterations of gradient descent until you get to, say, hopefully a good local minimum. Okay. So this function that you're trying to, this loss function, this empirical loss function, is a highly nonlinear function. Okay, and not going to be convex, right? And the various reasons, even if you start off with a quadratic square loss, for example, because of all the nonlinearities in the network, you're going to end up with something highly non-convex. Okay, but it turns out that gradient descent really works well, or actually a form of gradient descent called stochastic gradient descent, which we may have some opportunity to talk about towards the end of the course. Works really well in producing good weights for the neural network, right? And at least there's a lot of empirical evidence. People are trying to develop a theory still for why gradient descent work so well and producing good values for your W and B that actually allow you to do a very accurate machine learning in many applications. But yeah, so that's still an open problem, a hard theoretical open problem. But in practice, it seems to work really well. Okay. Any questions?
Hello, Professor. So for the previous part, when you said that each layer we have multiple neurons, and at the end, at the nth layer, you like usually we just end up choosing one layer. So how do we boil down to just choosing one layer from multiple neurons in the last?
One neuron in the last layer is what I was saying. If you just want a scalar output.
Okay, but
depends on the application. But in most applications, you would like just a one-dimensional output. So you have a very high-dimensional input. So D can be very large, but you may only want to have one-dimensional output. Like say that you're trying to predict the home price of, that's the example I gave you, based on a lot of input features like crime rate and pollution level and so on and so forth. Right. So in that case, basically, you would force your neural network to produce just one output at the end. So it'll be only one neuron at the last layer.
So you just get rid of all the remaining last neurons and just.
I mean, but the number of neurons in each layer is really up to you, right? You can choose as many as you want, or as few as you want, and the number of layers is also up to you. It's a design choice.
Okay.
So just because I might start with a very high dimensional input of 1 million, and my first layer I might just have 100 neurons, for example.
Okay.
I could do that.
Okay, makes sense. Thank you.
And then maybe increase it in the middle and decrease it again, and come back down to 1 neuron at the end.
Okay.
It's a lot of engineering here. There's not much theory to. It's more what should I say? Yeah, there's not much. There's not a strong. I mean, there's again empirical evidence that certain kinds of networks work well for certain kinds of problems, but there's no hard and fast rule about how to choose these things beforehand. Okay.
All right. Thank you.
What makes stochastic gradient descent stochastic?
What's meant by stochastic gradient descent?
Yes.
Good. So here, basically, I can just give you a high-level idea right now. So you want to compute the gradient of the sum, right? And that'll give you one step in my gradient descent procedure. So what is in stochastic gradient descent, rather than using all the samples, all the samples, and producing one gradient step with respect to all the samples, you might take a subset of the samples. Say I have 1,000 training data points. I might batch those 1,000 training data points into say 100 batches of 10 each. Okay, and then basically compute the gradient, one step of the gradient, only using those 100 data points only those 10 training data samples to compute one step. And then for the next step, I'll go to this second 10. Okay, so I'm actually changing the training data points that are being used in each step of my gradient descent. Okay, and that's called stochastic gradient descent. And it's a special case of a more general notion of stochastic gradient descent, actually. And it turns out in practice that doing it that way allows you to avoid local minima that are bad. But that's, again, empirical evidence for that. Okay. And then, again, the convergence properties and stuff. I mean, that's a different story altogether. So what does stochastic gradient descent converge to? And if the function is convex, for example, does it converge to the same thing as your original gradient descent converges to? And these are all interesting theoretical questions that have been studied. Okay, we may have a chance to talk a little bit about that towards the end of the course. But this is the first course in optimization. So there are other courses that you can take in the university that talk about those kinds of problems, okay, in more detail. Any other questions?
One more question. Why would you use one neural network function over another?
I couldn't hear that question. Can you speak up?
Why would you use one sigma instead of another?
So that's again a design choice, right? So you try out different choices, and some sigmas work well for some applications, and others work well for other applications. So typically, when machine learning, if you want to determine, which choice you use, then you use a procedure called validation or cross-validation. So you try out different choices and see which one gives you the best so-called prediction error from. But this is not a machine learning class, so I'm not going to get into the details of that. But if you took a machine learning course, you would learn how you can actually make a choice between or choose between different options, basically. But there's also a theory that's been developed for choices of sigma in terms of function approximation. So there are certain choices of sigma for which you can actually prove theoretically that if you have enough neurons that you can approximate an arbitrary function with some. You have to impose some constraints on the function, but you have results like that. So okay.
Okay, thank you.
Yeah. Okay. All right. If there are no other questions, I guess we can stop, and I guess I'll see you on Thursday. Yeah. Okay.